Hello, welcome to a new video. In this video, we're going to talk about mixture of experts. So in the last video, we finished up attention. And in this video, we're going to look at mixture of experts. As you see here, we set the feed-forward network of our transformer block to this mixture of experts class, which is defined up here. There's a bunch of parameters, but the one I'd like to call out are this. So as you can see here, we have an expert start index and expert end index. And what we're doing is we're doing expert parallelism where different GPUs have different experts. And it's branching based on the rank. And then today we're going to go through the forwards method of this mixture of experts class to build intuition. And then in future videos, we're going to go through the gate and expert classes themselves. So let's get started. Conceptually, what is mixture of experts? The idea is that you're going to have a token. And what we're going to do is we're going to run it through a gate. And that gate is going to tell us of our n experts, in this case 4 experts, which of the k experts we should send it to. In this case, k is 2. And so maybe this token gets sent to expert 2 and expert 4. And then we're going to combine it. And when we combine it, we're also going to learn a weighting. So we might say, oh, we want to take expert 2's answer with 80% weight and expert 4's answer with 20% weight. And then we're going to combine them. And all of this is learned, the routing to figure out which experts to send it to, and also the weighting. And then the other thing to note is that this is on a per token basis. So if you have a sequence of, let's say 5, 10 tokens, the different tokens might get sent to different experts. Yeah, so that's a high level what MoE is doing. Now let's look at the code. So the first thing we do is this x.view -1. What is this doing? What this is doing is it's flattening the batch and sequence dimensions. So previously you had dimension 2 through 4. Now you just have 6 by 4, where that first dimension is now this flattened batch and sequence. What happens next? We go through this self.gate. And what this is going to return is weights and indices. And the way to think about these return values is indices will correspond to, for each token, which experts it should go to. So for example, for the first token, if we get back 1, 3, it means that we want to route this to expert 1 and expert 3. And what weights represents is how we should combine the expert output. So in this case, for token 1, we want to combine it with 80% of the expert 1 response and 20% of the expert 3 response. Next, we see that we just allocate this Y tensor. This is going to be our accumulator tensor, which we'll see later on, where we're going to add intermediate results to this tensor. Next, we have this counts equals torch.bin counts, da 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 da. Morally, what this is doing is it's telling you for each expert, how many tokens are going to get sent to it. So for example, if you have this tensor, after you run this, you're going to get something that looks like this. And what this means is that expert 0 will get 2 tokens, expert 1 will get 4 tokens, etc., etc. We now iterate through our experts. You'll notice that we're using those indices. And so different GPUs will iterate through different indices. And if there's no tokens, then we just continue to the next iteration of loop. Otherwise, we're going to do some token routing. So this is pretty straightforward. This is the part that is perhaps non-intuitive, so let's spend some time on it. Okay. So conceptually, what is torch.where doing? Conceptually, the way to think about torch.where is we're going to iterate through every single leaf element in your tensor. And we're going to run this predicate, okay? So for example, in this predicate, it's saying indices equals I. In this case, indices equals 1. And morally, what we're going to do is we're just going to return a list of coordinates in your tensor where this predicate is true. So for example, let's take a look at indices. So indices looks like this, right? And we're saying what elements are equal to 1? Well, if we do the coordinates, we see that 0, 0 is equal to 1, 1, 0 is equal to 1, 3, 0 is equal to 1, and then 5, 1 is equal to 1, right? See, these are the coordinates into the tensor. And indeed, if you look here, this is what gets selected: 0, 0, 1, 0, 3, 0, and 5, 1. And what torch.where does is it returns a tuple corresponding to each dimension. And so IDX corresponds to this first dimension, 0, 1, 3, 5. And as you see here, 0, 1, 3, 5. And then top corresponds to the second dimension, 0, 0, 0, 1. And that's why you get 0, 0, 0, 1. Okay, so now what happens next? Now we're going to add to our intermediate accumulator tensor the output of running our tokens through this expert. And remember, this torch.where has selected the indexes of the tokens we want to run through the experts, and also given us like the indexing into the weights. So after this, basically the experts have added their intermediate results to our Y tensor. Then afterwards, we do an all reduce, because remember, like we're sharded across all the GPUs, and so we need to do an all reduce to bring it back together. And then lastly, we will always add an additional shared experts intermediate computation, and then we return. So hopefully that was useful. Hopefully that builds high-level intuition as to what's going on. And in the next video, we're going to talk about this gate, and we're going to talk about what's actually going on within the experts. So see you in the next one.